Okay, thanks. So thank you for the opportunity to present this. I will talk about Quake and the multi-node scheduling. And first, I will just want to clarify one thing. At the beginning of the project, we have entered with the tool Hyperloom, but I'm now talking about the Quake. And one of the things that I want to explain is why we have decided to create a new tool and what are the differences. But both of the tools are generally related to the workflows. So you have some acyclic graphs that describes the computation. Dependencies are basically between the tasks and some produce data. So some tasks may produce some data, some other tasks may consume it, but it's usually described on the level of abstraction, just on only these dependencies, not where the computation should run. It just describes what should be executed. So it's not fixed on a particular machine or size of the cluster or anything like this. And there are tools like the Hyper tools, PyComs, Quake that they are dedicated to run this type of description on a specific machine in some efficient way, do the distribution, load balancing, and stuff like this. So in particular, in case of the Quake and Hyperloom, it works like this, that there is a part which we call the client, where the user composes the graph in some Python interface. So basically it calls the functions in Python, and it creates a graph. In the background, it creates the graph, and then this graph as a computation, as a plan of the computation, is sent to the server. The goal of the server is to look on the graph and do the scheduling, decides on which computational node the computation should run, and distribute the initial data and the computation itself. And then the workers, it's the processes on the computational nodes that actually executes the computational itself. Workers also communicates directly peer-to-peer in our case, so there are no bottleneck in terms of distributed file system. So if you do not touch the file system, also our system will not do this. And all connections are basically peer-to-peer. When the computation is finished, the data are sent back from workers to the server, and then from the server to the client, which may decide what to do with the result, maybe just submit another plan or print the results or whatever you want. So this is the basic scheme. This is how looks the API. This is just some import. You have some function. You annotate the function that this is that it tells this is just the Python task, and it's just create a constant. This calls the functions, but instead of executing the function right away, it will just make a note. Oh, I need to run this task, and it will just create a note into the task graph, not executing it right away. And when the task graph can be composed from this small calls to something big. When task graph is finished, you can submit it and wait for the result. And the Hyperloom is one of the tools that can execute task graphs like this. It was very focused on the low overhead, so we have like less than milliseconds overhead per task, counting even the composition in the Python or communications and so on. You can schedule like more than 1 million of tasks. We have lots of optimizations to avoid copying, especially if the computation is on the same node. We have strong support for the external programs, and we can do CPU management. But for the ExaQUte project, one of the important things is to run MPA applications, and it is something which is not implemented in the Hyperloom. So basically, are missing multi-node tasks. So yeah, it seems like natural step. So just let's implement this thing. But yeah, actually, it's not that easy, because what I want to show you is why the scheduling of multi-node task is actually more tricky than just the scheduling task that runs only in one node. This is one problem, and also our scheduler is heavily optimized for this particular scenario. But most of this feature is quite is not needed basically for the ExaQUte. Like low overhead, if you need to start MPI program, it will take like hundreds of milliseconds just to start the MPI daemon. So it doesn't make sense to hunt every sub-millisecond optimizations. Also, the task graph, if you have a multi-node task, are usually not that big as if you just manage lots of on CPU level tasks. Also, lots of optimizations between the tasks because of the MPI cannot be done because the MPI daemon is started again, and it would need some extra tricks. We have some prototype, but we are not using it ExaQUte because it has some restrictions that it was not possible to use it. Also, external programs is not needed, and the CPU management. If you have if you are scheduling on the nodes, you don't care about the CPU management, and you are on completely different level. But first, so this was the reason why we did not want to modify this heavily optimized scheduler to something very different, while we do not use these optimizations. It will be just the obstacle. So yeah. So what about the scheduling in general? In task scheduling, the problem is that in general, task scheduling is NP hard, even for very, very simple instances, like on small number of nodes. If you know everything in advance, there are no communication prices and so on, and it still can be NP hard. So in practice, you cannot hope that you will get an optimal solution. But the good news is that in heuristics works on the practical examples works very well. We have also implemented a simulator where you can try different heuristics on different network models and in different situations. And for practical cases, you can find quite good heuristics that is relatively simple and it works in many situations. So in some sense, for the single node scheduling situation, it looks like solved. But let's look on the multi-node scheduling. Here, it's just very simple graph. You have just one task that produces one piece of data and another task that just consume it. And this hexagonal thing is just the worker. So let's assume that the task one will execute it on the worker one. And so the data is now lying on the worker one because it was produced there. And now we have to decide on which worker the T2 will be executed. And basically you have like just two options. It will be on the worker one. Then you can just run it as it is, or it will be on different worker, and then it will just you need to copy the data, just this data. So the cost is known. That there are just two situations, and everything is simple. But in case of multi-node scheduling, this is just this situation, but now the task one is MPI applications and it runs on the several nodes. So let's assume that it works. This guy was executed on worker one, this guy was executed on worker two, this guy was executed on worker three, and produce some data. And there is now the following task will need is MPI applications on two nodes, and it also has some dependencies. But now the decision on which worker we should run the MPI rank 0 and MPI rank 1 is not so clear because it very depends on how these dependencies are and what are the sizes of the data and so on. And this is the problem. So let's have a particular example. So let's assume because the arrows here is quite clear that this guy will produce one data, this guy will produce one data, and so on. So the complexity always lies in the second part of the image. So just take the second part of the image. Let's assume that the data one has the size 20, whatever unit, gigabytes, megabytes. Data 2 has size 10, data 3 has size 13. And now I have to decide on which node I should run rank 0 and rank 1. And let's assume that this is the state of the cluster. Like worker 1 has the data 1, but it does not have data 2 and data 3. Worker 2 does not have data 1, but it has data 2 and not the data 3, and so on. And this table is just the different notion of these dependencies. Like process 1, this circle, needs data 1, data 2, and does not need data 3, and process 2 does not need data 1 and needs data 2 and data 3. And what is the goal? The goal is to find some mapping, like map the process 1 to some worker and map process 2 on some different worker. But what is the right solution? Like, for example, if I will map process 1, which is this pattern, on the worker 2, I see that, okay, the worker 2 already has data 2, so it's good, and we do not need to transfer anything. But data 1 is not here, so we have to transfer them, and the cost is 20 megabytes of the transfer. And now if let's say I choose this, then I have to choose process 2 will be some different worker, and I will also pay some costs if I will not find some exact mapping. Of course, if I would map process 1 to worker 4, there will be 0 cost because all data are already there. And then I have to still choose something for process 2 and so on. And now the question is, what is the optimal solution? And it's not one natural thing would be, okay, let's minimize the data transfer. It looks like a good idea, like take all the data transfer, sum them, and find the minimum. So we will just minimize the sum of the costs. But the problem is that, the good news is that it's weighted perfect matching problem, which is quite well-known problem. And even the simple greedy algorithm does not work. Actually, it's in polynomial time. So it looks like the solved problem. But actually, it's not like this, because the minimizing the sum is not the right way. And I will now show you why. Let's assume the following example. Data 1 has cost 30, or size 30, data 2 30, data 3 10, 10, and data 5 19. And I have this kind of pattern, like process 1 wants these guys, and process 2 wants these guys. And this is the layout of the cluster. So worker 1 already has the data 1, and data 3, and so on. And now, what is the optimal solution? So in case of the perfect weighted matching, there is the following solution. Let's map the process 1 to worker 1, which will look like this. Process that, I just basically taking this line and putting it here. So yeah, the data 1 is already there, data 3 is already there, but data 5 not. So this will cause the cost of data transfer is 19, and process 2 is mapped to worker 3, which is like this, and it already has all the data, so the cost is the 0. And this, you cannot find a better solution for this. But actually, there is another solution. It looks like this, that I will map the process 1 to worker 3, and it will look like this. And I have to transfer the data 3, which is cost 10. Now I want to map process 2 to worker 2, which look like this. Again, I'm missing this guy, which each cost is 10. And so the total cost is 20. So it's worse than 19. But actually, it's better solution because there are different nodes and they can download the data in parallel. So optimizing the minimal sum of the data transfer is not a good one, because the things can be downloaded in parallel on to different machines. So what we actually want to minimize, at least it's not still ideal, but it's much better to minimize the maximum of each data transfer for each worker. So basically, they download, the guy who needs to download the most is I'm minimizing this. And yeah, it works better. Yeah, but how we can compute it? Actually, if I will put some another realistic constraints, it's quite easy to show that it's also NP hard. So again, we cannot hope for some exact solution. one option could be, okay, we have a polynomial algorithm for something slightly different for the sum. Maybe we can use it as a proxy. But yeah, our experiments on some realistic graphs shows that it does not work quite well as a proxy, because it's still it's not that cheap to compute it, and the results are not that good. So using the perfect weighted matching is not a good idea. But fortunately for the real examples, you can also use quite simple greedy heuristics that works relatively well, because what is the situation in practice? This thing can be quite wild because it's the state of the cluster, and previous computations can quite shake of the whole state, and different workers has different data. But actually, this pattern is usually quite regular. Like in many cases, it's just some simple diagonal, or it's just the or is just the full matrix or something like this. So because of this, this is quite regular. Some quite simple heuristics works in practice, and this matrix basically means that these dependencies are not usually too wild. So what we can do, but so we have implemented some heuristic like this, but still think it that we are just scheduling on the higher level of the task graph. We are scheduling this simple shape. We have just one task that produces one data part, and it's consumed by another task. But this graph can be also quite complex. It may produce more outputs. It can be consumed by different tasks and so on. And you still have to solve this problem on several layers, and you need to somehow combine these two heuristics. That one that is doing the scheduling on the higher level of it is something that is doing the scheduling on this inner task level. And this is the reason why we have decided to create a new scheduler from the scratch, basically, that is prepared especially for these tasks. And it's slightly slower, but yeah, as long we are not hunting every millisecond, so it's quite okay. How it looks in the end? Let's assume that I have a case like this. There is some my preprocess. This is just some function that runs in one node. It produces for data, and now I want to run MPI program that runs on the 4 nodes, and for each node I need different part of the data and also some configurations. For the native, this is the native API for the Quake, but we have also implemented the common ExaQUte API. But I will just show you the one way. It's very similar to the common one. This my process needs one node and produce 4 outputs. This guy will run on the 4 nodes, and the data is scattered, and by default it is basically broadcast. So here I'm just doing the broadcast, so I don't need to specify what is the parameter configuration, and the rest is just I will just start the computation and gather the result. Yeah, how it look in the future? This is right now we have several tools, but they have a different schedulers, backends, and we want to somehow make some things together. Now we are developing something what we call TACO, which is some unified scheduler for the things that I have shown you. But we don't want to unify the API. Like we have still the Loom API for the more or less black box task, Quake for the MPI task, RSDS for the Python task, which actually implements the Dask API, and some meta scheduling. And we believe that they are quite different tasks. So we don't want to create one API for all of them, because then I will just put the burden of one use case to another. But it looks like that there are, if I want to use Loom, I don't want to usually need some things from the, let's say, MPI scheduling, then, and vice versa. So we want to have separated APIs to make them as simple as possible, but have some common platform that is in background, and and we reuse the code and so on, but basically it's hidden from the users. Yeah, so this is all from my side. So if you have any questions.